All right, deep divers, welcome back. Ever thought about rain? Like, really thought about it? What if rain didn't just mean clouds, but actual power for your home?
Exactly.
Today we're diving into something pretty cool. Rain-powered solar panels. It's this hybrid tech that, well, it aims to turn soggy days into watts.
hmm
And we're looking at places like Bowling Green, Kentucky, where this could be, really relevant. So let's unpack this. How do these panels actually grab energy from the sun and the rain?
Well, the core idea is pretty neat. It's a two-pronged approach. You've got your standard silicon solar cells doing their thing with sunlight. A typical efficiency, maybe 14 to 20%.
Okay, the standard stuff.
Right. But then layered on top or integrated are these things called triboelectric nanogenerators,
Uh-huh.
TNs for short.
Thanks, okay.
And these are the key for the rain. They capture the kinetic energy when raindrops hit the surface. It's basically using that liquid-solid friction to generate a bit of electricity.
Friction from raindrops. Wow.
Yeah. And what's really clever is this DVD-inspired design they're using. Think of the grooves on a DVD.
Huh. Like actually grooved.
Exactly. Tiny grooves on the polymer layers. And this isn't just for looks. Get this. The grooves increase light absorption for the solar part by about 10%.
Okay, a nice little boost.
But for the rain part, it increases the energy collection by something like 400% compared to just a flat surface.
Whoa, wait. 400% just from grooves.
400%, yeah.
Yeah.
It dramatically increases the surface interaction with the water droplet. So you get panels that work in sun and rain. They kind of self-clean with the water flow. And importantly, they can plug into existing solar setups.
That DVD design, it's not just clever, it feels like a real breakthrough. A simple physical change with that much impact, 400%.
It's a great example of bio-inspired design, really.
And you mentioned Bowling Green. With what, 55 inches of rain a year on average? That's a lot of potential friction.
Precisely. It makes it a fascinating test case. All that rainfall is just, well, potential energy falling from the sky that we currently don't capture. And their weather profile fits too. Not much hurricane risk, maybe a bit of small hail sometimes, but generally suitable.
Okay, so the tech sounds promising, especially for rainy spots. But let's talk brass tacks. What about the cost? And does it, pay off?
Right, the economics. So an estimated 10 kilowatt TN hybrid system might run you about $28,700 up front.
And traditional solar.
That'd be closer to $23,940 for the same size. So yeah, it's a bit more expensive initially.
Okay, so the payback time is probably longer.
It is, slightly. We're looking at maybe 19 to 22 years for the hybrid system to pay for itself versus around 17 years for traditional solar in that area.
But you get energy even when it's raining.
Exactly. That's the trade-off. You get an estimated 8 to 12% energy boost during the rainy seasons, plus, over the lifetime, potentially greater reduction in co-Eurolus emissions.
Interesting. Is there, like, a real-world example?
Well, we could look at the Richardsville Elementary Solar Project. It's an existing project. If you hypothetically added TNGs there, based on their weather, those extra 45 or so rainy days a year could add another 4,200 kilowatt hours.
Okay, so about a 2.7% annual increase.
Something like that, yeah. And it builds on infrastructure that's already proven itself. They had ballasted roof mounts that held up in 58-mile-per-hour winds, which is a good sign for resilience.
Okay, so benefits are there, but it costs more, pays back slower. What are the sticking points, the challenges holding this back right now?
You're right, it's not all smooth sailing yet. A big one is the durability of that 10 layer.
How long does it last?
Current estimates are maybe 5 to 7 years.
Okay.
Compare that to the solar cells themselves, which last 25 years or more.
Yeah.
So that's a significant mismatch.
Yeah, that's a big difference, replacing layers every few years.
It's a hurdle. Then there's the electrical side. Tend to produce a pretty low voltage, like 2 to 5 volts. You need to figure out how to efficiently combine that with the higher voltage from the solar cells.
Right, voltage matching. And anything else?
Well, those grooves we talked about, they do add thickness, maybe about 30% thicker panels. And then there's the local economics. In Kentucky, the electricity rate is around 11 cents per kilowatt hour. That relatively low rate just stretches out the ROI.
And I guess no specific subsidies for this kind of hybrid tech yet.
Not currently, no.
Oh.
So state incentives aren't really helping push it forward at the moment.
Okay, so durability, voltage matching, cost, lack of specific incentives. Quite a few challenges, but what's the feeling? Is this going somewhere?
Despite those hurdles, yeah, the outlook seems pretty positive, actually.
Yeah.
There's talk Bowling Green might pilot tinning integration in some city projects as soon as 2027.
Really? That's so.
That's the target. And they could leverage research partnerships. Like Tsinghua University has this interesting bridge array design for tangs that could help with scaling up.
Okay.
Plus, the city isn't starting from scratch. About 12% of municipal buildings already have roofs ready for solar, and climate trends. Spring rainfall there has actually increased about 6% since 2015.
So the potential resource is actually growing.
Kind of makes the case stronger, doesn't it? You combine their, 2,800 sunshine hours with 174 rainy days. This tech could genuinely help create a more balanced renewable energy supply.
It really flips the script, doesn't it? Rain stops being the enemy of solar power and becomes, well, another source, turning that hindrance into a resource.
Absolutely. And imagine scaling this up. By 2030, maybe we see this tech really starting to change how cities think about energy, making every single downpour part of the solution. It's about balancing sun and rain.
It definitely makes you think. So wrapping up, what does this mean for other places? Maybe places even rainier than Bowling Green, or just any city trying to squeeze energy out of every possible weather condition. Could this fundamentally shift how we define renewable?